Sometimes it happens that when you
Okay,
leave
now,
and rejoin, it comes.
okay,
Sir,
then,
can you, the down, you have that right hand side box, no? So can you just minimize it? Lower down. Ah, yes. Thank you,
okay,
sir. Thank you. Thank you.
okay.
Yes.
So, good
Yes.
afternoon. Let us begin our second session. Uh, if you have remembered, the first session, I explained all those things: pattern, machine intelligence, relevance of soft computing, data mining from pattern point of view, then impact of fuzzy sets, impact of artificial neural networks, feature relevance, then genetic algorithm, then rough set theory up to this much. So emergence of rough fuzzy computing, if information granule and then case mining. Of course, I will repeat a few slides for your just continuity. Yeah? And then today I'll be explaining this granular computing application of those one, then how to integrate different tools for multispectral image segmentation as an example, then judicious integration of all those soft computing tools. Emergence of soft computing will come every time. Example of integration, generalized rough sets and entropy, that's very important. And then application to image and video analytics today. As I don't know, let's see how much I can cover. Okay. Now, before that, if you remember, last time you asked a question that how can it be, how they are really relevant to pharmaceutical industry, right? So let me make some points clear. In the pharmaceutical industry, right from drug discovery and development to manufacturing, marketing, in all facets, all aspects, AI can be implemented. Keep it in mind still. From that means in research and development, R&D wing, where you will be having discovery of drugs, and then manufacturing of those drugs, then marketing, because without marketing, the manufacturing has no meaning. So in all aspects, AI plays an important role. For example, what are the ultimate gain? Ultimate, we like to have the companies can make all business operation efficient, cost effective. That's most important for any business, and then hassle free. Let's consider Let's consider, for example, drug discovery. So drug discovery is the process by which new candidate medications are discovered. Everybody knows. Now this involves learning from chemical data, predicting properties, 3D protein structure, designing molecules for new molecular structure, optimizing synthetic routes, then target-based drug validation. So it involves tasks like learning, designing, optimizing, and then validation. If you look at this, all these tasks, advanced AI and deep learning have a reputation, as I explained so far, for all this learning, prediction, and then your design, optimization. Here, optimization means genetic algorithm, learning means neural network, predict means neural network. Similarly, design means any kind of techniques involving AI. Then advance all those AI and deep learning tools, they make them easy life, and that have until now the difficult to solve. Because today, without AI, it is very difficult to solve all these problems. But once you use advanced AI tools, including deep learning, then you make their life easier as compared to what we have today. And more importantly, after you discover the drug, it needs to pass some trial, clinical trials. And here it is very expensive because as per an MIT study, only 13.8% of the drugs get successful in clinical trial. So therefore, remaining percent, they are all wastage. So to reduce this cost, here comes the adoption of AI that improves the success rate of new drugs, create more affordable drugs and therapies, and more importantly, reduce operational cost. Similarly, for manufacturing purpose, its purpose is to have higher productivity, improved efficiency, faster production of life-saving drugs. And this task involve quality control, predictive maintenance, where you can use AI tool technologies, waste reduction, design optimization, process automation. And here AI basically enables pharmaceutical companies to launch drugs in the market at faster and at cheaper rate as compared to the conventional time-consuming manufacturing. Similarly, in marketing, you keep in mind that it is through only marketing that healthcare providers and patients can be influenced into prescribing these medications. Unless you do not find any patients for clinical trials, then your medicine cannot be sold out. So therefore, here AI has a big role, for example, in finding patients for clinical trials. And for this purpose, one simple way, you use artificial intelligence or pharma companies can explore, develop unique marketing strategies that promise high revenues and brand revenues. And that means you, based on the previous marketing strategies, you retain the most profitable one. That means it's just searching method. Then you design the present marketing method campaign accordingly, thereby you reduce the time and save money. So here you use behavior mining, link prediction, community detection. That means you need to predict which product will be much sellable to the community. So that's how accordingly it's called a community detection problem in online social network. Similarly, link prediction problem, that means which one will be most important product after 6 months, which is not so much productive at this stage. So that is link prediction. Today you do not have that link, but you are expecting that after 3 to 6 months that link will grow one. So this is called web-blind and problem. So these are a few examples I mentioned. Similarly, other than this, other AI-based healthcare services include diagnosis based on knowledge-based real-time prediction, just like medical doctors. They have their old knowledge base, etc. They create new knowledge base, they store everything, and then a new doctor, a patients come, they retrieve from this one and then use it. Similarly, they can predict a monitoring epidemic outbreak based on the previous examples. Similarly, you can have remote monitoring based on Internet of Technology. For example, when you have a heart patient at a remote place, you can see monitor the signal of the ECG, and then you can prescribe the medicine accordingly. Similarly, for other mobile-based application, that means you use AI-based healthcare service by pharmaceuticals companies, health providers, and etc. There are so many other ways. Basically, keep in mind that AI machine learning means you are based on previous experience. So if you have more previous experience, you can have better result. Then AI machine learning means you have to have the learning mechanism. Then AI involves your design, optimization, optimality, uncertainty modeling, and so on. So wherever you have all those characteristics, your AI will be very much useful. I hope it's not clear. Now, let me come to refresh what I taught in the last part of the one. I explained what is fuzzy information granule using rough rules. I explained the simple example with a toy example. This is a concept or region or class, whatever you believe in, and given this granulated domain, low, medium, high, this is arbitrary, you can choose other way. I can see that this region or this concept or this class, whether it is labeled or unlabeled, that means whether you know its source of origin or you do not know, RoughSet has capability in encoding with the help of this rectangle. And this rectangle means nothing but this rule. First feature is medium and second feature is medium. And so that means this rule represents some region. So if So this is a compact object. If the object is elongated, then you get more than one such rule, more than one such. And this rule which characterizes this region is called granule, information granule. So once you have information granule, you can throw away the other information, and based on that, you can call it information representation, class representation, you can call it a case representation, you can call it a granule, and so on. And most of the data mining problem for which you do not need exact precision, you can start from here. If you need exact boundary for retrieval, then you can start from one. So by this way, you save lots of time. And as I mentioned to you, if you have more than one, it's elongated, you have more than one such granule. Now, again, as I mentioned before, here both the features have appeared, but in real life problem, all the features may not appear. That means it leads to dimensionality reduction. I will show. And accordingly, I consider it a case or prototype or granule. Elongated clusters need multiple rules. That means one class can be represented by more than one such granule. And we call it case generation, not selection. Why? Because out of 2 for 1, we generate a rule. Here the dimensionality is 1, but in real life problem, dimensionality can be reduced. But if I make a feature selection, then that means it will be a subset of this set, but with the dimension remains the same. So that's why I call it generation, not selection, as it involves dimensional reduction, and also it may involve variable dimension reduction. That means all the classes may not have same number of reduction in dimension. It's called variable dimension. Therefore, it is less storage requirement. That means by storing capacity is less. Therefore, my retrieval will be very fast. Therefore, it will be suitable for mining large data sets. Rough case generation, I explained yesterday, the other day, that from this one, how did I collect these rules? That is, class 1 is characterized by this conjunction. F1 is and this or this. That means a class is represented by so many regions. If conjunction represents a region. Therefore, each conjunction represents a region, and for each conjunction we store, or what we store, the membership functions. That means central point and bandwidth, central point and bandwidth, and I put the label class 1. So that's my case. This is class information, and I give the membership values of these functions which appear in the rule. And every class may have more than one such rule. And this is the structure of a class, parameter of the membership function, center radius of the membership function, and class information. These are the typical membership functions. So if you look at this low, medium, high, we give sufficient amount of overlapping so that the result that we get is just much more valid. As I mentioned the other day, these are the two granules which can be characterized from the two classes, and I have only this membership and this membership for this membership and this membership. These two memberships do not appear. So therefore, when I have stored these regions at the cases or the classes, and I get a now unknown, for unknown we only compare with this first feature low and second feature high, not with medium. Similarly for this the one, and then I retrieve that class to which it has got maximum similarity. So this was my feature value for low, medium, high, low, medium only, high, medium one. Then I retrieve that class. That means I compute the similarity only with respect to those membership values which have appeared in the rule, not for all membership values. And that's how I reduce the time also. Now, I make in when you have these classes, the next question comes, how can I say that my cases are much more efficient than the other one? Because there are many other machine learning algorithms. For example, if you have simple random, you just pick up one sample from one. That is also the case. So now, when you want to compare, otherwise your idea will not be accepted by the reviewers, publisher. So what do? You compute the evaluation in terms of say 5 independent parameters. That means the parameters which are not dependent on your methodology. First of all, you check the using 1NN classification accuracy, how much these cases that we have obtained are powerful in classifying the remaining sample. That means training set 10, and then you see how many of 90% test set gets classified with the help of those cases. Similarly, number of cases stored in the case base. That means how many cases you require to store to just represent a class. Similarly, average number of features required to store a case. That means there are so many cases, what is the average number of features required? Similarly, CPU time required for case generation, then average CPU time required to retrieve a case. These are typical some parameter machine learning parameters we are using. Now, let's consider iris data as an example. I do not know how many of you know, when you work with machine learning, this is the first data usually you are given. What is the iris data? It's 3 flowers, iris flowers, setosa, versicolor, and virginica. And you have 50 flowers from each class. And what are the features? Sepal length, sepal width, petal length, petal width. So there are 4 features. There are 50 samples, that will be 150 from 3 classes, and there are 3 flower classes. These are the typical flower, iris flowers, setosa, versicolor, and virginica. And if you look at this petal length, petal width, sepal width, if you look at this one, and now if we draw the scatter plot in say sepal length, sepal width, sepal length, sepal length, petal width. Similarly, petal length, sepal width, sepal length, all those. Now, if you see that you take 2 together from out of 4, you get 6 combination. You see in every case, if you notice it, there are 2 flowers are overlapped, but there is 1/3 flower which is quietly apart. Here you see, here you see. That means our intuition says that you no way need 4 features in order to segregate the 3 classes, 3 flowers. Because for this flower, and 1 feature is enough. For example, this sepal petal length equal to less than equal to 2. Similarly, here also 2 features are enough to segregate this. Similarly, here 1 feature, sepal length less than 0.5. So you can see that one. Similarly, for here, that is, since only 2 classes are overlapped, for which you may need all those 4 features in order to segregate them as much as possible. But for the 3rd feature, you need only 1 feature. So on an average, you no way need 4 features per flower. This is our intuition, and this is what is you got verified when you compare with random method. That is, you pick up 1 flower randomly, just 1 flower blindly from every class, 3 flower. So number of cases we take 3 for all cases. Rough fuzzy, then it is instance-based learning. David are very popular, highly cited, and there your number of dimension remains the same. And then it is a modified one. Here it is a number of dimension changes. So see, average number of features required to store a case means flower. Then the classification accuracy of this flower based on this case, 3 cases. Similarly, generation time. Similarly, retrieval time. So look at this here for all the methods. IB3, IB41, you need all 4 features. That will be petal length, petal width, sepal length, sepal width to store a flower. But here, for the proposed one, you need 2.5. So you can see that, as I mentioned, that all the 4 dimensions, all the 4 features are not required to store all the flowers. That is called variable dimension reduction. Therefore, on an average, you get 2.5 features you require to store a case. So there are 3, 1, so 7.5 instead of 12. So with the help of this reduced number of feature dimension, still you get maximum classification accuracy. Very interesting. Randomized method, almost zero, because you pick up randomly one method. So there is no time required to generate, almost zero. Second one is the previous one. And since you have average number of features required is minimum, so your retrieval time is also minimum. And for others, retrieval time is maximum. So this is for iris flower representation. So you can see that how efficient it is to represent those 3 flowers. If you take forest cover types, there are 10 features which are cartographic and remote sensing measurements of 7 wood classes in the forest. There are so many samples. Here also you see this proposed and the one modified David has instance-based learning variable. There it is set, but it is retrieval time is first is 1NN classification accuracy that is still larger than this one. Similarly, for here you can see generation time here almost zero. It is second one, and since it is about only 4 features out of 10 features on an average you need, so the retrieval time is same. Here also almost same because they are one. However, with this help of this, you can see that classification accuracy 1. So this shows the superiority of 1. And here number of cases 545. That means out of 7 classes, we have 545 samples. Or here also our rough fuzzy, the granule also 545 total. So that your comparison becomes fair enough for all methods. Now let's compare that. So far we have explained all those granule, right? Information granule. Now based on the information granule, let's define granular computing. That means you now perform all operations based on the granule. And you just forget about individual data points. So what is granulation? First, let's consider what is granulation. Then we'll define granular. Granulation is a task. So what is this? Basically replacing a fine-grained universe by a coarse-grained one, more in the line of human being, like perception. For example, when you look at a scene, as I mentioned you before, the previous session, that when you look at the scene, what you see basically, your eye goes to the some region of sky, some is grass region, vegetation, some water body, some habitation, and so on. So basically, you replace a fine-grained universe by coarse-grained one, more like with human perception. That means it is a process like self-organization, self-production, morphogenesis, Darwinian evolution that are abstracted from natural phenomena. And with the help of granulation, you generate segments, clusters, which are called granules. So in the process of granulation, natural clustering, you generate clusters or segments which are called granule. So granulation is a process of formation and representation of granules. This is very important. Now having these granules, the concept of granule, for example, so it is a mathematically it's a clump of indiscernible entities. That means the objects that you cannot discriminate, cannot differentiate with respect to some properties, say similarity, proximity, functionality, and so on, with respect to given attributes. So it is a clump of indiscernible entities with respect to given attributes. Indiscernible means you cannot segregate in terms of similarity, proximity, or functionality. For example, granules in age, granules in direction, school, example. Age. What is it? We call very young, not so old. So here this is a granule. That means I am not going by the age 30, 25 or 21 or just 22.6 years or something. I call by say very young. So that is understood that it could be from 15 to 25, 25 to 35, depending on the context. Similarly, direction, when you drive a car, you go by slightly left, slightly right. You do not measure the degree and then you turn. Similarly, in a school, each class or section can be called a school. Each class or section in a school can be called a granule, because that section in the class is determined either by age group or by marks obtained in the previous class or by sex and so on. Similarly, in an image, if you look at this, there we have got 6 consecutive day levels: 1 to 6, 2 to 7, 3 to 8, so on. And as per Weber's law, our naked eye cannot discriminate. So we call it, I can call it a granule. So here, if you look at this, I have given different examples of granules in case of age, direction, one. Now, some of the granules, they do not have well-defined boundary, just like very young, slightly left. That means boundaries are fuzzy. But here, boundaries is crisp. It's a hard set. Here, boundary is crisp, 1 to 5, 1 to 6, 2 to 3, 7, etc. Therefore, in real life problem, granules could be crisp or fuzzy, depending on the problem. Now, having these granules, whether it is crisp granule or fuzzy granule, granular computing means it's an information processing paradigm that works with the process of information granulation abstraction. That means you have extracted information granules, or you are abstracted information from the data, and then you perform the computation based on this information granules, not data point. That means you forget about data. Whatever information you have extracted in the form of rule or in the form of any other set or equation, then you perform all operation based on this. So, since this information granulation abstraction, that is basically compressed information, compressed. So since you are playing with information compression, granular computing leads to computational gain. So it's called suitable for mining large data sets. Granular computing, in summary, it's a nature-inspired information processing paradigm with the basic elements called granules. Just note it carefully. And what are granules? Granules are collection of indistinguishable objects which may be drawn together in terms of some characteristics or properties like similarity, functionality, physical proximity, etc. And more importantly, the granules evolve in the process of abstraction and derivation of knowledge from data. So granules could be adaptive, granule could be changing also. Not necessarily it is fixed. So these are 3 key points to define granular computing. So next question comes, there must be a role of granule, because granule represents all the information. Granules represent the abstracted information of the data. Therefore, varying the size and shape of granules will determine different levels of granularity. That means finer to coarse. Characterize a specific aspect of the, it depends which aspect of the problem you want to play with. So you define your granule accordingly. It represents the model differently. The different models can be represented by different ways depending on the size and shape of granules. Similarly, you regulate the decision-making task accordingly. That means depending on the granular size and shape, you can regulate the decision-making task. So all depends on the size and shape of granules and your need. Therefore, granules play a significant role in granular computing. Now, it may be noted, the concept of granulation is inherent in the theories of fuzzy set offset. For example, the membership function that I mentioned along x-axis or y-axis, this type of function that represents a granule. So membership function itself, membership function is the building blocks of fuzzy set. Practically, it granules the features. That in the feature axis F1, F2, F3, it produces this kind of function. So granule produces fuzzy granulation features. Similarly, rough set theory concerns with a granulated domain. That means crisp set defined over a is granulated domain. I will explain again the theory. So, though the name is granulation, but basically granulation first was coined by said theory Professor Lafizade in connection with defining membership function. And then Professor Pavlov has defined a set defined over a granulated domain. But the word granular computing was not coined that time. That has been coined recently by after just before 10 years or so from different communities, including my group at Indian Statistical Institute. Therefore, fuzzy sets and rough sets are most successful technologies for granular computing. Therefore, you will see that in the literature, 80%, 90% literature or granular all related to either fuzzy set or rough set, mostly rough set theory, because that itself defines the granulated domain, where a set, each set has been defined. Now I'll explain some application of this graph granules. I explained application of ICET, application of neural networks, application of generic algorithm. Now I'll explain some rough granules because you have now fair idea about the granules. So what we can do, there are so many applications. First of all, case-based reasoning, that you evidence when your data is sparse, you do not know the distribution, etc. Say medical doctor, you go to one. So what do? They do not go by the distribution of the cases. They have stored some of their previous patients' symptoms. That is their cases. So it's called case-based reasoning. That means you make reasoning and decision based on previous cases, not based on any kind of distribution or anything. So when evidence is sparse, you go by case-based reasoning. That's why case-based reasoning becomes so popular. One, for example, when you move to a different city for the sake of your job, what do you want? You are looking for a house. So what do you do? You just go to an agent, real estate agent. So they ask your requirement, money, etc., and then they show you some kind of case examples and you select. Similarly, law interpreter also. So it has so many applications in case-based reasoning. Then prototype generation, that the granules that we have extracted, that can characterize a class I mentioned you. So that can consider as a prototype generation for class representation, particularly when you have data set large in dimension size. So it leads to dimension reduction and data mining. Similarly, data compression, because that equation or the rule that you extracted, rule that itself a compressed information for storing. Similarly, more importantly, clustering and image segmentation were key. See, clustering, image segmentation, clustering is an unsupervised problem. Yesterday, last time I told you, again, it's challenging because you are given the entire data, entire image, but you are asked to partition the image into meaningful region or the entire data into some meaningful pocket. Now, you do not know number of clusters, so what do you do? You assume some key. Number of clusters, let it be 2, 3, 4, and then you segment. Now, every time you have different number of classes, you have different output. So therefore, clustering image segmentation is an unsolved problem where you do not know the number of K, number of classes. So here RAPSEC theory helps you because RAPSEC theory has a capability, whether the data is labeled or unlabeled, to extract the granules, number of granules. So if you have the number of granules 3, then number of cases I can consider 3. I can start from K equal to 3 and then start working. So K is very useful. I will show some result. Similarly, knowledge encoding in neural network. That means once you have those rule from the data, I can encode those in neural network. So the neural network starts from a better parameter values than the raw. Therefore, learning time will be reduced further. Similarly, this is a good research topic, granular information retrieval in heterogeneous media, because in text, hypertext image, as in www, so that is a good. Now I'll show some example of rough set knowledge encoding or expression maximization. Many of you might be knowing EMA algorithm, statistical approach, and minimal spanning tree graph theoretic model for multispectral image segmentation. Again, segmentation is an unsolved problem. That's why you can still deal with this problem today, particularly when you have got heterogeneous and large data sets. So what is EM algorithm? What are the merits? As we know, it can handle uncertainty out of overlapping classes, because it is based on statistical probability theory. But the problem is the number of clusters needs to be known. If you have different number of, you start with different number of K, you get different number of solutions. So solution depends strongly on initial condition. But it can model convex cluster because it is based on Gaussian. So this is the plus point, this is a minus point also, convex cluster. That means irregular shaped natural cluster, it cannot model. But it can handle uncertainty out of overlapping classes arising from probability of occurrence of arising from randomness. Now we have got graph theoretic approach, minimal spanning tree clustering. What is the advantages? It can model non-convex clusters. That means any type of shape, irregular, natural cluster. But it is very time consuming. On the other hand, rough set theory knowledge encoding, we have seen it can automatically detect the number of K clusters, because I have shown, given a data set, how to use rough set theory to find the number of regions, that is the number of granules. Therefore, K, I have an idea that provides good initialization. So therefore, avoidance of local minima, faster convergence, and I can use computation granular. That way, I forget about data. I work only based on these granules. So granular computing, therefore, I can reduce and take care of this time-consuming part. So if I make a judicious integration of this rough set knowledge encoding plus EM plus minimal pairing tree, we have automated determined number of clusters. We can model non-convex clusters with less time because of granularity. We can also model convex clusters. We have uncertainty handling from overlapping classes and so on. That is all these advantages I can see if we can make it through integration. This is very popular. So therefore, let's consider a remote sensing IRS. There are 4-band images, blue, green, red, and infrared. So out of this, I make granules, 8-dimensional. So this is my all rules. Rules generate all these granules. Now, when I know this number of granules, I can consider K equal to number of these granules. So I can define Gaussian, that is mean covariance matrix. Mean covariance matrix, all from 1. And then I use expression maximum algorithm, that is splitting margin. Splitting margin. Then I use minimal spanning tree where the node corresponds to each of these Gaussian. So I get arbitrary shape regions. Very interesting and simple technique. Now you see multispectral IRS image band. We have got blue, green, red, and infrared. 4 bands have different signatures. So if I integrate, because no band is individually capable of identifying those regions, That's why we need multispectral image. And we use, for example, beta index defined by us. So what is beta index? Suppose you have got C number of regions. Given the C number of regions, you compute this ratio. That means overall image regions and for a particular class, ith region, you compute the numerator. Similarly, you compute the denominator based on every ith region. Therefore, n is the total number of pixels in the image. Mean value of the image x bar, mean value of nth real values of ith regions, that is xi bar. So for every region xij, I compute its difference from mean value of image and mean value of ith image. So I take this ratio. Obviously, my higher value of beta is desirable because higher value of beta means this is larger, this is smaller. This is larger. This is larger means this from homogeneity is more within a region, and between an overall originality, it should be, sorry, overall homogeneity is more, and within class homogeneity also more. So if you look at this one for a number of C, if C is the number of regions, then you can see we like to have higher values of numerator and lower values of denominator. Higher values of denominator means your difference from every region from the total mean value of the image should be more high and it should be more less. That means here homogeneity is more within a region, and considering the entire image, homogeneity is less. So this should be more, this should be less. Similarly, now consider all kinds of algorithm. EM, that means you use random initialization plus EM. You use random initialization plus k-means. You use rough set theory initialization plus EM. Rough set theory initialization plus k-means. Then you use k-means initialization plus EM. Then you use random initialization plus EM-MST. Then at more fuzzy k-means. Then at last rough set initialization plus EM-MST. So all these permutation combination, if you look at this, we compute the beta value and a number of bands 4 and final number of clusters, we found 5. So C equal to 5. For this, you see the improvement of EM by REM, improvement of KM by this by this. So beta index from here to here improved, here to here improved, and here to here is improved. So there are all kinds of improvement of beta value when you use rough set theoretic on the other of EM, on the top of KM means algorithm, on the other top of EM plus MST. Similarly, if you go the competition time, it reduced from here to here, here to here, here to here. So significantly, so you have gain in index value, you have gain in competition time. Similarly, look at the some resulting image. This is for beta equal to 5.91, 5 equal to 5. Segmented value is using EM algorithm with rough initialization. EM algorithm with random initialization. That means this one. EM algorithm with random initialization. For this, and with respect to this, we compare this one. Here shows the 5.91. Here it has increased to 7.37. So now look at the difference. Here, this bridge on the river could not be detected. Here you see, bridge of the river could be detected. So, and also these other segments also become much more prominent. So this reflects our intuition. That means higher the value of beta, better is the segment quality. Of course, for a given number of cluster C. If the C changes, then it will for a fixed number of C. Similarly, for zoomed version, if we make it, here we cannot discriminate the bridge segment. Here is bridge. Here is railway strip, runway, airport runway strips. You cannot segregate nicely, but here you can nicely segregate. So rough setting is the EM algorithm plus K. So this is the comparative results by visually. Now, so far I have explained the individual relevance of these tools so far for pattern recognition and mining problem. Rest of this. Now, next question comes, what a challenge in judicious integration. How to make judicious, because every tool has its limitation. As I told you before, fuzzy set has limitation because how to find the membership value parameter we don't know. ANN has limitation, how to find the initial parameter value and how to choose the number of nodes and layers we do not know. Genetic algorithm has limitation, but genetic algorithm can help to overcome the limitation of all these techniques. Similarly, rough set has certain merits also, which can be used. I will show how to reduce the limitation of ANN and so on. So challenging issues is soft computing integrations for judicious. Now, in late 80s, scientists thought, why not integration? Because neural network revived in early 80s. I told at the beginning. So then, since neural network has so many advantages, but at the same time limitation, I mean, fuzzy set also has some advantages and some limitation also. Genetic algorithm also and so on. Therefore, scientists started thinking, including me and in my group, that why not integrations? Fuzzy logic plus ANN. ANN, GA, all kinds of permission combination researchers started doing and started publishing, including from Japan. But out of those, neurophagy hybridization is the most visible realized one. That's why you see in the market neurophagy vacuum cleaner, neurophagy camcorder, neurophagy refrigerator. Now, what is neurophagy? That means you integrate the neural characteristics into fuzzy logic or the other way. So what is this? Why neurophagy fusion? Because fuzzy set theoretic models try to mimic human reasoning and the capability of handling uncertainty. That was our lesson we have seen. Similarly, independently, we have seen neural network models attempt to emulate architecture and information representation scheme of human brain. That's what I explained in my last slide, that it tries to mimic the biological neurons. It tries to mimic the information representation scheme of human brain. It tries to mimic the nervous system. So if I can consider fuzzy set theoretic as to build the software, neural network can be considered to build the hardware. Therefore, if you can make judicious integration, I can call it a neurophagy computing for generating more intelligent system. That means the intelligent system that you cannot achieve by using these tools separately. You can only use one. That's a very standard logo we derived in late 80s when I was working at NASA Johnson Space Center, Houston. So this is a neurophagy integration. Now, when we integrate the teeth, there are two things I don't know. Neurophagy. You have in the market fuzzy system. You buy it, you don't touch. By step, and you artificial neural network for learning the rules and adaptation. It's fuzzy system. If A then B, if C this fuzzy system. If low then high, etc. You use artificial neural networks to learn this algorithm. It's called neural fuzzy system. On the other hand, you have ANN in the market. You buy it. But ANN has a limitation that it can take input only in 0, 1 and output also 0, 1. But we can use in the real life problem, we can see that input could be linguistic, input could be fuzzy. Similarly, output also could be fuzzy because the output is overlapping. Therefore, I use fuzzy set theory to augment its application domain. That means in the input, I can use in the output, I can use it in the training. So this is what is called fuzzy neural network. This is called neural fuzzy systems. So in the literature, when you see neural fuzzy systems, that you have fuzzy system available for market. You use artificial neural network to tune its parameters. And when you come fuzzy neural networks, that means you have ANN in the market and use fuzzy set in input output to augment its application domain. Just like I explained the other one before, I will again explain some other models under this category. So when you have merits, you have merits of integration two types: generic merits, applications merit. Generic merits means that you inherit, say, neural network properties, adaptivity, robustness, ruggedness. So when you have neural fuzzy systems or fuzzy neural network, you inherit all those characteristics. So there is no challenge. Challenge comes how to achieve application specific merit. That means the merit which you could not achieve by using those technologies separately or alone. There lies the challenge. I'll show this is a challenge in this is an 1994 it is an outstanding paper out by the Neural Network Council. This is multilayer perceptron. I buy it from the market. But then I see that it has characteristic that it can generate nonlinear boundary, highly nonlinear boundary. So this is very much essential for any kind of pattern decision mining problem. Now I take from the market, I see that it cannot accept. So in order to augment its application domain, I take input low, medium, high, so that it can accept linguistic input, it can accept the numerical input also. Similarly, the output, it used to have 0 and 1 only, but now I can say it can have fuzzy also. Therefore, and also I can see that since we have fuzzy output, that instead of 0, 1, mu1, mu2, mu3, all values lying between 0 to 1, instead of either 0 or 1. So I can make the gradient descent search for parameter correction from output through input, depending on the membership value at each one. That means I pass it through all values rather than only one value having value 1 and others are 0. So in this way, I can see that my boundary oscillation will be reduced, and there is a possibility of getting stuck to local minima that will be reduced. That possibility will be reduced, but not removed. So I can have low, medium, high at the input. I can have output overlapping. I can have the gradient descent search technologies based on the all individual nodes, depending on the membership values. That be higher the membership values, be higher correction, lower the membership values, lower correction. Therefore, it handles imprecise input, handles uncertainty arising from overlapping classes. If backpropagated errors are assigned appropriate weightage depending on mu values at corresponding output. It can handle linguistic input in addition to those by conventional multilayer perceptron. So this is called under fuzzy neural networks, because you haven't touched the neural network. You have bought it from the market, but you have played here and you have augmented it. So this is a typical vowel diagram in Indian Telugu vowel. It has got 6 vowel classes, 2 features just to show the intricacy, complication of this feature space. So much overlapping with this class, this class, this class, etc. Only 2 features I have taken, but it has another dimension also, F3. Now look at this one. Speech recognition problem, 6 vowel class, classification score, base classifier 79.2%, neural networks, nodes in each layer 10, 20, and for hidden 10 nodes in hidden layer, and there are 5 layers I have taken. Testing time, training time. During training time, you look at this conventional method, MLP means only 0, 1 it can take input. Hard linguistic means if you give linguistic, it makes it hard, either small or either medium or hard. And fuzzy means all membership values are there. So you can see that during training, it has 86 as maximum 1. Similarly, during testing, it has got 84. Though it is almost close, but it has advantage that it can have 20% linguistic patterns, which these 2 terms, these 2 models cannot handle. Therefore, this is the merit of this scheme. That's why it is paper received in at that time. Paper was accepted in 1992, and in the 1994 it received the outstanding paper award. So, note, one is important note that this was the paper I mentioned to you, outstanding paper award from one. Now is the note that although Zade formally defined the concept of soft computing in 1994, this is the expression. publication for soft computing. But all the different challenges of synergistic integration of its individual tools were addressed much before that, since 1990 or before. For example, this paper 92, we started working in 1888, 88, 89, because it takes to publish a paper from India 2 to 3 years that time, 3 years. So this is an example. This is how to make synergistic integration, and this synergistic integration were attempted by different researchers from all over the world before the term soft computing was coined by Professor Jade in 1994. So many people do not know this. So I thought better I stick to this. This is the one. Our government of India established the Center for Soft Computing Research, a national facility at ISI in just 2004 under my leadership. There, under its IFA scheme, innovative intensification of research in high priority area. That is a very prestigious scheme of the Department of Science and Technology, under which they established center around a distinguished scientist who has already established research credential in this area. So now, similarly, lately realized rough fuzzy. Rough fuzzy was not that time. It's a relatively much newer topic. Neurophagy is much more older topic. Rough fuzzy, because rough set was not introduced as a soft computing tool that time. One, so we have a big contribution to this aspect. Rough fuzzy computing, a stronger paradigm for uncertainty handling. So what is rough fuzzy? Fuzzy set theory, as you are now expert, you can see that it assigns each object a degree of belonging to represent an imprecise, vague, or overlapping concept. And similarly, on the other hand, rough set theory, the focus of rough set theory is on the ambiguity caused by limited discernibility of objects, lower and upper approximation. Therefore, we can have judiciously integrated to develop a model of uncertainty stronger than the either one. And this was the first book we published from Poland. My counterpart, Professor Andres Kovron, was a student of Professor Pawlak. So rough fuzzy hybridization, new trend synergy in 1999. That means we have the granulated domain. This is my fuzzy boundary set. So these are the questions. So it has about 12 edited chapters written by all pioneers, which handles the different ways these communities can be integrated and so on. So accordingly, we have got emergence of soft computing, as I mentioned, because first is a rough set, etc. Now, what is soft computing? Just to have a simply refresh, to exploit the tolerance for imprecision, uncertainty, approximation.